Hey guys, and welcome to the full course on Fundamentals of Computational Fluid Dynamics, your gateway to mastering one of the most transformative tools in engineering simulation and design. This is a certified course, so make sure to fill out the form in the description after completing the session to claim your certificate. You can proudly share your achievement on LinkedIn to showcase your new skills. At Skill-Lync, we are dedicated to offering advanced, industry-relevant engineering courses crafted by industry experts. Don't forget to subscribe to our channel for more insightful tutorials and updates on engineering tools and techniques. Hit the subscribe button and stay tuned. Here's a brief overview of what we will cover in this training video. In the first module, we will discuss the basics of physical testing and virtual testing, and how CFD has transformed industries by making simulations a reliable and cost-effective alternative to traditional methods. You will also learn about the importance of CFD in modern industry and the key outcomes you can expect from mastering this skill. In the second module, we will dive into computational fluid dynamics itself. We will explore the underlying principles of flow physics, break down the CFD process, and show how this simulation technique solves real-world engineering problems across industries. You will gain insights into critical concepts like flow separation and boundary layers, which are fundamental to understanding the aerodynamics and fluid flow behavior. In the third module, we will address challenges in CFD such as computational costs, managing turbulent flows, and accurately simulating real-world conditions. You will learn how to navigate these hurdles and ensure reliable, accurate simulation results that meet industry standards. In the fourth module, we will explore the career prospects in CFD and the exciting opportunities available in industries like automotive, aerospace, energy, and healthcare. You will also gain insights into future challenges and trends in CFD, including advancements in simulation technologies and emerging applications like renewable energy and medical research. Thank you so much for joining us today. We are thrilled to have you on this learning journey. Make sure to subscribe to our channel for more updates and detailed tutorials. Complete this session, earn your certificate, and proudly share your achievement with your network. Let's get started with fundamentals of CFD and unlock your potential in this groundbreaking field of engineering.
Morning, everyone. In this session, I want to make something, in fact, very clear. We are not going to study what is computational fluid dynamics, because 3 hours of class or a crash course or a workshop is way too short to introduce, in that. But the fact is how computational fluid dynamic is involved into the industry. What is the importance? What is the background? So I'll be touching a lot of areas, including the applications, including how the construction happened, what is the phenomena, what is I would say the certain rules behind computational fluid dynamics when we talk about, with a lot of example, and the future aspects in the career. What are the current challenges, and what could be the job profile also. So again, we are not going to have a room, what do you say, is classroom class, but first we will try to understand what is the need of computational fluid dynamics, the virtual simulations, how they stand, how they help into the industry. So that's why we have kept the topic, and the name of the topic is computational fluid dynamics, resolving fluid physics computationally, because here we are taking computational resources, uh, you know uh, the sum of equations, some principles, some laws. So everything here is a part of computation, how we are dealing the virtual the virtually. So let's start the session. Okay, so what I have done, I have splitted the whole presentation into some modules. So in the first module, where we want to understand the physical testing, how the testing is in reality or how it is done. We're not going into the detail of what type of different testing, but the physical testing, what are the factors, and then the virtual testing, because that's a need, why it is required, why what is the importance into the industry for the both for both type of testing. and what is the outcome, how industry utilizes the both testing modules or both testing facilities for the product development, or maybe for testing, or maybe for validation or verification of the product. So we will have a short talk on that also. Basically, this is where uh, the computational part, or the virtual simulation or virtual testing parts comes into the picture. Then into the second module, we will talk about the computational fluid dynamics. We'll be talking about how what is CFD first of all, and some of the very important parameters, not in hardcore detail, but yes, core detail. Some of the things like which are the laws, which at least we need to understand when we are dealing with computational fluid dynamics. So because I have a good experience and very good grip on the automobile and aerodynamics and thermal management, so I'll be taking a lot of example from automobile, and most of you are from the mechanical engineering background, so you will be able to understand that very well. And next, we will try to understand what are the challenges in CFD, what are the different types of challenges in terms of development, in terms of CFD development, like the code or the solver or the software itself, a tool itself. And what are the challenges in industry? In past few years, we have seen there are a lot of new products are coming. The manpower has been reduced, the automation has been increased. So what are the challenges, what are that those challenges? We will see those things. And in the last module and the final module, we will see what is the job profile you can get. That's a very normal question whenever a person do a certification course or learn CFD. They want to understand, okay, which industry or what is my role into the industry, what kind of work I can do for the industry, if I have learned a tool, or if I have done a course, if I have done a degree, what type of the job profile or the work profile I can look for. And then the future challenges includes in fact both for the industry, what could be, how we can use the computational fluid dynamics, or uh, how it will be helpful for the industry or the future aspects. Okay, so let's start the module 1, in which we will first try to understand the physical testing and what is the need of the virtual testing. So to make it more interesting and more informative, let's try to see how a physical testing is done. So I'm going to start a video which is basically a video from the NASA, where they have tested the rear wing of uh, uh, aircraft. So what I want you people to figure out or try to understand, how much effort is made when you're doing a physical test, when you're doing a real test, when you're doing a test with a real object. Try to understand how much effort has been done, what is the cost, what are the different machineries has been used, uh, how much the effort has been made. So I'll just start this video. So we have seen how a physical test is done for a wing. So now what we need is a real model. We The wing was really heavy. It was not this, in fact, scaled. It was one-on-one. The real wing of the aircraft, and we need to have a facility to accommodate the model. If the model is really huge or gigantic, you need to have such uh, facilities to accommodate that. Plus you need to have a heavy machineries to handle that. Infrastructure, of course. You need to keep where you're going to do the testing, the energy resources, because the test was done in the wind tunnel. So first of all, you need to have a structure of wind tunnel, and which is the most costly part of the aerodynamic testing. It cost billions and billions of rupees, because you need to have a big suction fans which can create or generate the velocity which is more than 100 kilometers per hour, or maybe that the requirements depends on the type of test you're doing. The manpower is most important part, because uh, not everyone can do a wind tunnel test. So you need to have a highly skilled professionals. They need to understand. They put a lot of, you might have seen there are a lot of computers, a lot of systems where the people were monitoring a lot of plots, how the the pressure is varying, how the physical quantities are varying on the wing when the flow is coming. And those things are not those skills are not very simple skills. It's not just welding, or maybe it's not that simple. You need to have very good hands-on experience on that, because this kind of this kind of test you are not going to repeat. It's one time. In fact, it takes a lot of energy, it takes a lot of cost, it takes a lot of effort. So you need to have skilled professionals who can properly capture all those things without any issues. Probes to capture the physical parameter, yes, because you need to have some sensors, you need to have some probes. We are well aware of those to capture whatever the physical quantities you are interested in. Most probably it's the pressure or the velocity contours, not the contours, but the variation what these sensors will check. So you need to paste all those probes or sensors on the wing, on the object properly. And one drawback of this is it might affect the flow also. It's good to put, because there is no other way. You cannot check, you cannot test. But in reality, the wing is smooth. In reality, when the aircraft is in the air, they don't have any the probes, they're in fact smooth. But when you're doing a physical test, you need to capture those parameters. So you're putting the probes that might disturb the flow physics near the wing. So it's a kind of risk, or you can say tolerance, where you need to understand how much variation you're going to get from the real test. Then you have computers and machines to capture the data. Of course, this is very sensitive thing, because and this should be error free also. If you have to connect all those probes or the sensors to the computer, so you need to have a good machinery, you need to have good setup of computers, resources which will capture the data properly. Again, cost and the manpower, so you don't have to repeat the test, so everything should be error free. Hazardous situations, which is really 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 important, because human life is precious. You cannot indulge, you cannot go into the physical test where there is a probability of getting hurt, or maybe life or death. In that case, you have seen there are a lot of heavy machineries when they were moving the wing from the outside to the wind tunnel. So all those things are very dangerous. So handling those situation, are we safe? So all these things brings a failure limit also, of course, because you need to understand the human. You if you're doing a test, you cannot just think, okay, at what point it will fail, you don't know. And if you are into the environment which can hurt you, it can, it can harm you a lot. So failure limit we need to understand when we are doing a physical test. uh, so all these things, what we have seen from the physical test, that brings a lot of cost, a lot of cost, billions of money. uh, and then the safety, which is another very important parameter. So we have seen a one set where the physical test has, of course, you get the feel of, how the flow feel or how the result looks like, how in reality it might, yeah, you might be, how it might, perform. But again, at what cost? If it is, if you are developing a product, uh, where in fact you are testing a billions of money just in the development phase, or I would say the testing phase, it might, not be good, because maybe the product cost is not that much. And of course, the end of physical test, it's not that you do in one shot and you say, okay, we are done, we are good, those are the perfect results. No, there is always a scope of change. You will see something, scientists will see something, designer will see something, simulation person will see something. So physical test has some limitations. If we These are two main points which I figured, which I try to put, which is most important. Now we will try to see what is the virtual simulation. So I don't have to introduce what is virtual, introduce what exactly is virtual simulation or virtual test. Virtual test is something we create, a virtual environment in our computers, and we do the testing. Why I said the virtual test? Because not just computational fluid dynamics is one part, or one, what you say, is a branch of virtual test. The structural, the electrical, any part, any simulation, any type of physics we are trying to solve on our computers with, creating a virtual environment for the product. The virtual test is, it's some CFD is just one part of computational fluid dynamics, where we deal about the flow, maybe the thermal, also the fluid flow, in fact, right? So CFD comes into one part, but the virtual test, what in fact is virtual test? So what we are doing is we are creating a virtual environment for the product. In reality, how it will behave when a consumer or somebody is using, or what exactly is the functionality of the product. Okay, then what we do is we try to replicate the physical test, with the help of, some laws, with the help of some physical setup. We try to build a setup which should be, of course, which should be validated computationally also, whether it is giving a proper result or not. Is it following all the physical principle or all the certain laws, principles? Say for example, the Bernoulli's equation, if you're trying to set up something virtually, a pipe flow or a pipe, so is it following all those things? So these things, how we try to give in terms of, the equations where we are solving the virtually. We know very well that for any physics, for any kind of principle, we have certain equations, so kind of hand calculations, but those equations you are converting into the into the, the virtual format, or the computational format, where we solve it based on the principles. And then the add-on variable, of course, a simple problem will have a simple variable or a straightforward. Maybe when you want the more complex problem, you need to add a lot of complexity into those problems, add-ons, in fact. And then on the virtual test, we need to run certain number of iterations, or certain, certain number of cycles for the performance, certain number of rules. Say for example, when we see, okay, the convergence has been reached after such a certain iteration, the result is not changing with, with the field, when we're talking about the steady state simulation. So there should be some criteria where we can take those results. When we are solving the equations virtually, we need to understand at what point we should take away the results, or what is the extent where we can stop the simulation, and we can take those results for our reference. Limitations, of course, the real physics is much more complex than what we think, because if we just talk about the fluid flow near us, what we solve from computational fluid dynamics is maybe just 10%. It's much more complex and it's much more unpredictable. We cannot predict at all. It's impossible. Computational fluid dynamics can give you only a sense or idea that it could be or it may be look like this, but exact, no, not at all. Those solvers doesn't have a capability or capacity to solve that much or take that complexity. So we have certain limitations, of course. So what we do is we do those tests in that limitations and we say, okay, these were our assumptions, and if it is passing into certain criteria, if it is passing certain criteria, it will be able to handle the real physics also, but it's not foolproof. There are a lot of cases where the virtual tests were giving a result which is, you can say, acceptable, but the real physics were totally different, totally different. And we were not trying to understand, what is the correlation, how we can, correlate, because the results were totally different from the field and from the virtual simulation. So within those limitations, we would like to, bridge between the virtual simulation, virtual test, and the computational and the physical test also. So those are the limitations when we do the correlation studies. So that's limitation of virtual test. It's not just CFD, it's with all the virtual tests, with irrespective of any platform, irrespective of any physics. Now, the advantage what we get from the virtual test is, of course, the cost. You don't have to build a real model, or you don't have to build a real wind tunnel. Okay, so that saves a lot of cost. Of course, flexibility. If you do a model is dropping in your computer, nobody is getting hurt. It's perfect. You do any mistake in the model, in the CAD, nobody will be affected by that. So you can do the changes. So that's flexibility. And there are certain situations where you can perform the test. So you can take your computer at anywhere, so you can basically perform a test. So flexibility, of course, it's a big thing. Time, because the setup, or the time to take a physical setup, it's a lot, and you need to test those setup also. So the time, of course, with the virtual test, we save a lot of time. Quality, you can have a good quality. I would not say best quality, but you can do controls on the quality when you're doing a virtual test. Hazardous areas, of course, because if you are doing any simulation which involves like maybe more than 200, 300, 500, or maybe 1000 degrees centigrade, nobody is the simulation will be safe. Nobody is actually affected, and actually you can see what exactly is happening at 1200 degrees centigrade. In reality, if you are going to in a physical setup where the temperature is more than 1200 degrees centigrade, physically it's not possible, and it's risky also. Failure conditions, of course, if in reality we might not be able to understand that the failure limit, where it will break or where it will fall. So in those conditions, it will help, because we are doing virtually. Model behavior, of course, how model is behaving virtually, it's easy to understand, and add on parameters to see the complexity or understand the complexity of the test. Now, we have seen now two phases. The one is basically a physical test, where we have seen a video, where we have seen how the virtual test, how the physical test has been done. And then we see the virtual simulation. Virtual simulation will be talking about a lot, in fact, the CFD. So how industry are going to use that? So the virtual test has some limitation. Those limitations are maybe the performance you will be able to understand, okay, but not the potential of the product. Potential comes if you are trying to accelerate a car. You want to get the feeling now that pedal when you are accelerating, that maybe the potential, that's the potential of car, and that's the power of vehicle. That feeling or that understanding you might not be able to understand when you're doing a virtual simulation. The thrust of the vehicle, not just combustion, because it's combination of everything, combustion, and the power which is delivered to the wheel.
So it's a combination of a lot of things. So maybe the virtual tester can give you the performance. Okay, this much, if you're accelerating, you're getting this much power, but the feel, the potential of vehicle, you won't be able to understand. Some product must go undergo with the physical test, of course. The best example, the best of the best example what I can give is the tire testing. Now, wear rate of the tire is something which depends on the behavior of a driver or a behavior of vehicle. When the load is less, the load on the tires will be less. If the vehicle is heavy with the load, more load, so maybe the wear rate will be high. Those things you cannot test. Those things you cannot test virtually. In fact, if you see the drag races, or you say skidding of a wheel, or if you have an issue with the camber and caster, if you want to try to simulate how much the wear rate of tire is, you won't be able to understand physically. And in fact, till date, I don't think any tool is there to understand, or to give you a actual wear rate. Okay, this is the speed and this is the variation, so this much of thickness of or the rubber is getting away from the tire. So some products must undergo with a physical testing. Of course, the real physics is really complex, uncertain, and unpredictable. Even if you're going on a road with the tires, what we assume is we might have a road with a smooth or maybe the roughness factor for some part, but in reality it's totally different. We have seen on our Indian roads, it's really different than what we solve virtually. So for this also we can use example of flow near a car. As I gave example of the flow physics near around us, the flow, the air which is available around us, we think it's moving in one direction, because the problem is we cannot see those things, we cannot visualize those things. So if we can visualize, if there is a possibility to see those things, we'll be able to understand how complex it is, how random it is, how uncertain it is. So that I can say limitations of both, that for the certain products you have to use the virtual testing, and certain products you have to go for the physical test. Product development involves high cost. We have seen the testing of wing. Assume if that wing is not giving the good results, or in fact it is giving very bad results. So all the hard work moving that wing to wind tunnel, in fact manufacturing or the fabrication, that will cost a lot. Here we can see that computer models can handle infinite changes. If there is a issue in the wing, one surface is missing, you see some of the changes, some of the issues, you can handle it very quickly. But what is the outcome? What is the outcome of these two? So what industry is doing, because the physical tests are really costly and the virtual test has limitations, so what we can do is, the best arrangement can be done is use both. Now, how use both is, use the computational simulation up to the point where you are confident that yes, now I can go for physical test, where the virtual simulations where the real model is actually not available. You have a product idea, you want to see how the performance is, how the product will perform if we'll go into the reality of it, will go into the real environment. Till that we can do all the virtual simulation to understand how the flow physics is, because it's not just one iteration, a lot of iterations. We do one iteration, we did okay, we thought, oh, okay, so this part is creating a problem. What we can do is, we can either remove, or we can either modify this part as per the physics or as per the results we are able to see. So we did the changes, and again we ran the simulations. Now we see, wow, results are really better. Now we want to see, okay, let's do one thing, improve more, improve more, and let's see, now you're getting the best result. Wow. So that gives a flexibility, that gives the advantage of using virtual simulation. When you think now the product is final, I don't want to do any changes, whatever was my requirement is meeting, whatever was my requirement is now matching, Now I want to see how my product will actually behave in the on the road, how the vehicle will actually behave when we are accelerating, when we are driving. So that's the combination what industries are using, in fact, to save the time, cost, and of course the quality of the product. Some of the virtual physical tests are really impossible to perform. Say for example, uh, the combustion process. If you want to simulate a swirl motion in the combustion chamber, you want to introduce a new part, create more swirl. Now it's, suppose this is a heavy engine which is going to generate to 2500 of Celsius temperature. So in reality, doing that is okay. Maybe we are able to do a physical test, but will we be able to see how the flame propagation is happening? Combustion is very fast, within nanosecond or microsecond that happens, but you cannot stop that a frame. Even if you're capturing with the good cameras, you won't be able to understand, okay, propagation, okay, now if you do any change, you have to perform the test again. So the flame propagation from how that combustion starts, how that ignition is happening, how that uh, how exhaust are going out. So doing with the real test might be might create some issue. Or maybe the deformation of beam under pressure. So if you want to see the at the cross section how the pressure variation is happening, in reality it's not possible. Cut the beam and see how the pressure is variation at every node. No, it's not possible, and that can create a issue also. So the biggest advantage to keep the product under the virtual test until unless it's finalized, okay, then start performing the real test or the physical test for the correlation and verify that yes, my product is good now. But yes, we will have a deviations from the the computational test and the physical test. And what is the limit of those deviations? How much you want to tolerate that deviation? Tolerate means how much you want to accept, because of course the computational simulations are totally different than the physical tests. So how much deviation you are able to understand that, okay, I did think, or this much of deviation is expected. So that's the output of a virtual test and the physical test for any kind of simulation, for any kind of domain, or any kind of the virtual test. This will happen. This is the limitations, in fact, because putting the real physics into the form of the equations, it's not that way simple. You need to solve that. There are errors, there are the functions to handle those errors. So that is one thing, how the computational fluid dynamics, or the how virtual testing of flow and thermal came into the picture. That's a background of, in fact, that's the thing where you can say, why do you need computational fluid dynamics? The fluid dynamics, the fluid is very random in the motion. So you cannot just freeze a frame, or every time capturing with the camera. It's not that simple. Maybe the camera is capturing, if we talk about the flow in a pipe, maybe if the pipe is the transparent, maybe we are able to just see what is happening on the walls, on the boundaries, but in the core, the camera, no, it might not be able to see. So that's the need, that's the definition why we need the computational fluid dynamics. In fact, that's the reason why we are doing all computational simulation. That's the need for the industry, that's the need for the product development, that's the need for the quality of the product, and that's the need for the safety. So in second module, we are going to learn about, not learn, in fact, get introduced about the computational fluid dynamics. So here, what I'm going to show is some of the basic phenomenon, basic laws, basic, the idea how to judge computational fluid dynamics. Because initially I said computational fluid dynamics is not something we can understand in 3 hours or 2.5 hours of crash course, but I will try to make you understand what are the most important parameters which are involved into computational fluid dynamics. Maybe or not all the parameters, but for a simple physics, for a simple physics, what are the most parameters or the basic parameters which are involved. So now, a branch of fluid mechanics, which is of course which is based on the numerical simulation, because in reality on the background, which is the solver, there are certain number of equations which are solving. So those equations are, the Bernoulli's equation, as we know, and the mass conservation, energy conservation principles. So that's the background, or what you say is the concrete base of computational fluid dynamics, that they are based on the conservation of laws. So whenever you're doing any kind of simulation, those laws or those principles should be conserved. And that's the issue when you're solving the equations, because at any point, if those equations are not matching with the simulation, with the quantities, with the the input what we have given, it will diverge. In fact, not diverge, it will not give you the solution. Diverge is one word which is could be the technical for the tool, where you can understand, okay, there is something in my simulation which is causing a problem. If you're not aware of divergence, okay, let's not talk about divergence. Simple thing is, if any simulation you're doing, any problem computationally, if you're solving, if it is not able to solve the conservation laws, it will not give you result. So it will not give you result means it will give you some the message that there is a problem. But limitations where the problem is, because it's a vast the process, there are 3-step processes. So at what step you might have done mistake, or what input we might have given wrong, that we don't know, we need to figure out. Okay, so the important thing is these equations are based on Navier-Stokes equation, which is basically Newton's based on the Newton's second law. So collectively we can say, okay, we can say the Bernoulli's equation, which is basically a flow governing equation, mass and energy conservation principles, and Navier-Stokes equations. These are three major, only major, I'm saying. There are many laws, there are many schemes which are implemented into the computational fluid dynamics, but these three or these four are the backbone. Now, how do these equations or how these principles are converted work? Basically, we have a governing equations that we know for Bernoulli's equations for mass, energy conservation. There will be some certain derivation in certain conditions with some assumptions. So those equations, those formations, principles are converted into the governing equations. And those governing equations are again converted into the partial differential equation. Now, question comes, why partial differential equation? Why not algebraic equation? The thing is, in computational fluid dynamics, or I know much more about the computational fluid dynamics, so I'll take that example. Solving equations with the matrix with a lot of unknowns, it's way easier to solve when the inputs are in form of partial differential equation. If it is algebraic equation, it might not be able to solve it properly. So the partial differential equations, that's why the partial differential equations are used, because they can form a matrix which can be easily solved for computational, for the ease of computational, the calculations. Now, those solving schemes are some numerical methods, some the scheme. It's not only one scheme, there are a lot of schemes on which these principles work. So based on that, we get the approximate solution. Okay, why I said approximate solutions? Because we know when we started studying the Bernoulli's equation for the first time in our school, the first thing was the liquid is inviscid. But in reality, we know you take any liquid, even you take grease, even you take engine oil, even you take any oil or any fluid which is very slippery, I would say, but it has some sticky property. Okay, so we cannot just assume that the fluid doesn't have any viscosity. In reality, that's not possible. So we take some assumptions. Now these equations are also based on some assumption. When we are converting those partial differential equations into numerical form, we assume that things are like this. We assume that the temperature throughout the simulation or throughout the process would be like this. So these equations or computational simulations will be based on approximate solution. They will never give you exact solutions. They will give you appropriate solutions only. Now, why computational fluid dynamics? We have seen, a good example before that. Now, again, if let's take example of vehicle aerodynamics versus fuel consumption, where I want to do a physical test and I want to understand, how much the fuel consumption is related to if I have a vehicle which is not at all good in aerodynamics and the one which is very good in aerodynamics. Now the thing is, if you go for a road test, every time you go for a road test, you need fuel, because you need to burn the fuel to get the vehicle moving. Maintenance of vehicle, because of course, if your vehicle is not properly maintained, it might take more fuel, it might consume more fuel. So the vehicle conditions should be ideal whenever you go for a testing. The real test or the physical test, when you're going to do, the vehicle condition should be ideal for every time, because if any parameter is changing, it might affect the fuel consumption, it might affect the vehicle aerodynamics. In fact, if I say the simple thing, maybe the number of passengers, because that will reduce the height of vehicle, that might reduce the ground clearance. When there are 5 passengers in the vehicle, when we are talking about 1+4 vehicle, could be sedan or maybe the hatchback. So if it is fully loaded, all 5 passengers are there, the height of vehicle will reduce. In fact, not height, the ground clearance will reduce. That can affect the vehicle aerodynamics. So if you're going for the fuel consumption for 1+4 passenger, driver plus all passengers, so you need to have those parameters every time you're going, because the load condition will change, the ground clearance will change. So those things are, of course, you can do every time you're going on a road, you're doing those tests, so that will cost a lot. Now, the road conditions, driver's behavior, ambient condition, the weather today, it's windy. Okay, so today the air is moving opposite to the vehicle, so your fuel consumption will be high. The next day when you're going, the vehicle is moving towards in the direction of wind, which is, if we say a very windy day, so in that day you might have you might have the advantage of fuel consumption. And if you say the crosswind is there, so that can affect also the vehicle handling. The driver might have to ride the vehicle or drive the vehicle at low speed to get that better traction. Now, so those things are changing, those things you have to have constant, which is in fact not at all possible, every time. The only thing is how much similarity you can bring. And if you want to add some parameters, you have to repeat all the tests. So for that, you need to have a skill driver who can handle all those situations. Failure limit, of course, if you're going for 120 130 kilometers per hour, you have seen Indian roads, so that's a dangerous situation. If accident happens, skidding happen, or the failure happens in the engine, that might cause the issue. So those things again help us to understand why we can do the virtual simulations, or why we should do the computational simulation until unless our vehicle or the product is ready. And we can save the cost, we can save the we can save the the quality, we can save the time. And we will try to understand what are the parameters which are affecting aerodynamics, which are affecting the fuel consumption, because aerodynamics is one of the major thing will directly affect the fuel consumption. And fuel consumption is something which is directly related to the customer's pocket, the money. So that's the need of the computational fluid dynamics, again, to understand for the product development, for the the performance of product. In fact, now considering all those scenarios, is it possible to do a product development if you're going for the real testing? No, it's not at all possible. Geometry change, if you want to change every time, you have to do, and you have to perform a test. And one more thing is, test should be done for some cycle, at least for 2 to 3 times, because you have to have surety that whatever data we are getting, those are constant. If first time you did test and you say okay, results are okay, no, have you done the validation of your own test? If you perform the test at least 3 to 4 times, where the variation is happening, so how much variation you see? Some of the parameters, they will not change in the tolerance zone. It will be like say for example ±5. but it should be in those zone. If they are changing drastically, no, there is some issue in the test. There might be some issue in the machineries, probes, or maybe the digital meters you have kept. So again, are those things possible when you're doing all those things are possible when you're doing these simulations in the computational or the virtual simulation? Yes, without any issue. Okay, so let's take let's see one more video and try to understand how the computational fluid dynamics is actually helpful, not in just aerodynamics for the vehicle, but in many fields also.
Video highlights the benefits of using CFD modeling over wind tunnel testing for the analysis of wind in the built environment. Engineers, architects, planners, and designers must consider the effects of wind. In certain conditions, structures may experience vibrations due to wind. Pedestrians and cyclists in public spaces can be exposed to dangerous wind conditions. Traditionally, wind tunnels have been used to study across the entire domain. Models can be easily adapted and rerun without the drawbacks of scheduling time in a wind tunnel facility. Each of the models analyzing different wind directions can be run in parallel simultaneously. Furthermore, CFD modeling facilitates mapping of results in a highly visual and informative way, and can easily feed into iterations in the design process by exploring and comparing design options. In summary, CFD is an ideal tool for investigating wind effects, informing the early design stages, exploring and comparing design options, offering high-resolution input for regulatory compliance, and analyzing the wind environment in a fast and inexpensive manner. I'm Dr. Jennifer Keelahan from the School of Civil Engineering in University College Dublin.
So in that video, we have seen how Dr. Jennifer has, compared the wind tunnel test, what we were talking about, the real test or the physical test. Now, one of the most disadvantage of the wind tunnel test or the physical test could be where you cannot accommodate the real structure. You have to model it or you have to scale it. Now, scaling is not that easy, because the scaling of model happens because of not because in fact, with the reference of the wind tunnel, there are scaling factors, because scaling model doesn't mean you cannot you just know half the model or 1/4 or 1/10. It's not like that. You need to understand how much inlet velocity we are going to give when we are scaling the model. That's one most important thing. Now, scaling is one thing, and creating a virtual environment. Not virtual environment, the scaled environment near the model, how in reality it is. You need to understand, you have to do a study in terms of, in case you are going to do flow over a building, the pedestrian safety. You have seen how people were falling, actually how strong that wind could be, and that can create a lot of severe issues. I remember in one of the study or research paper where I was reading a Dr. Bert Blocken's blog, and I saw there was a case filed against the building because there are a lot of incident and accident happened in front of that building. The issue was that whenever there is a high wind, or the people were able to skid from the road, they were not able to walk properly, and that have caused the serious damage, in fact the death also. So you can understand the serious how serious it could be when we have a strong winds, and how especially in the places where we have high wind areas, maybe not in India, but the places where you can have the severe tornadoes, or maybe the high such kind of conditions. In that case, when you're building a skyscraper, in that case you are building a high-rise building, it's very important, because you should understand, or we should understand, how the wind would be, or how it will behave when it is leaving the the building or the side edges. That's serious business. That's really important. So that's where Dr. Jennifer has done a study of comparison of how CFD is really good. Even if you're going to do for a the virtual test, how much flexibility do you get? But of course, in some cases you need to perform the physical test. But again, the virtual simulation will help you what is important, what is not important. Based on that, you can do validation with your physical test. Now we try to understand what is the CFD process. It's not just running the solver. It's not that simple. It's not that simple at all. CFD is a process which involves the computational fluid dynamics, certain laws and principles. So before starting that, we need to understand what are the laws, what is the structure behind that. We need to understand those things, because see, we are human, we understand the physics. Computer is not computer is a brainless creature, or I would say it doesn't have a sense whether how it should work. So it will work only on the parameters what we are giving as input. So based on that only it will give you output. So we need to understand what are the things which are correct. We need to understand the principle. We need to understand the application areas. We need to understand where the simulation is possible, it's not possible, or what are the most important parameters which should not be skipped when we are setting up the case. So it's basically a 3-step process. Okay, the first step is the pre-processing. The pre-processing doesn't involve just meshing. Let me be very clear. I was taking a lot of mock interviews of the students where I was trying to understand how they break the CFD process, how they break the simulation when they're performing. And they always directly, 99% of the students, they directly start from the meshing. No, there is something which is before that, a tool. Meshing you do when you understand the meshing. Meshing is something you do when you understand the geometry and physics, because meshing is based on the physics. So before that, before using any tool, these are the things what I'm telling you. These doesn't require any tool. When you understand, tool is just for the input. So the pre-processing part is you understand the domain, what kind of physics you're going to solve. Okay, when you have a CAD, try to understand, is the CAD proper? Is the CAD or the geometry does have any flaws, any surfaces missing, any issues are there, or sharp edges, all those things you need to understand from the pre-processing. Understand the input. Input is not just, or initial input is not same as the initial condition. Input means for what you're solving, you need to understand, and based on that only you will set the parameters. I'll give you a very good example of why I'm talking these things. So next thing is the solver selection. So when you give, when you understood that geometry is proper, you set up the case, you gave the input conditions, you gave the initial condition that, this is how the simulation should happen. So the solver will take all those input. That's the scheme I was talking about. Those are the principle I was talking about in my previous slide, the physics assignment, all these things. So the solver will take all these input and try to solve. So the most important part is you have to choose a solver based on your requirement, based on the result you're solving for. If anything, it's like chain reaction. If anything is not right in that chain reaction, you will not get the proper result, or you will not get the proper output of that simulation or that solution. The last is analysis of the result, but I would say this is a very weak point, because what I can say is the analysis of the result are basically based on what you did. So it's just the output of whatever you have done. Let's see, this is what I can give you. So this is, I would say, least ignored part, or I would say this is the least part where at the initial state for the simulation, I will not focus on this. But of course, the result helps us to understand whether it's correct or not. Is it solving the physics as per the requirement or not? Now, we think the process is like this from up to down. No, that's not true. The process is actually like this. Now, how? Let me give you a very good example. You'll be able to understand properly. Now, everyone is aware of what is pizza. Everyone might have, gone to the restaurant and ordered. Now, the first thing is when you go to the counter, you say, you order, okay, I want a veg pizza. I want a veg pizza or a non-veg pizza where there should be some onions. I just want this kind of crust. I want this kind of toppings. I want vegetables. I want chicken, pepperoni, or whatever. So the thing is, you know what you need. So the end result, what you want to eat, you already know. That's the result, the final product. What you want to eat or what you want to get, you already know. You already know that. Now, what do you say to the executive that I want this kind of pizza? And then he asks you, okay, all these toppings, all these ingredient, what you took. Now, what do you want? How you want the cooking process? You want steamed, you want it, charcoal fry, you want a grill fry, or whatever you want. You said, okay, no, I want wood burn. So, okay, you got it. Now, at the end, you got the product. So the CFD process, it's same like, whatever we use in our daily routine. You know what you need, and based on that you have to set up a physics. Now, set up a physics means you need to understand what are the most important parameters involved into that, because anything, if you don't like, if you're vegetarian, if you order a chicken pizza, of course you're not going to like it if you're not going to eat it, in fact. So the thing is, you need to understand what are the inputs you're going to give, what are the inputs you want as the output. As the output, you want to see those results. As the output, you want to see drag coefficient of vehicle. So you will set up a case which will solve all the parameters which are directly related to drag coefficient calculation. If you're solving something which is not at all related to the drag coefficient, the calculation, you will not get the right drag of the vehicle. You will get some results, of course. If you change any ingredient in this pizza, of course you will get the pizza anyway, but it's not at all possible that you will not get a pizza. You will get it. But this is what you wanted, no or yes. That depends on you, how much you understand the process, how much you understand the product, how much you understand what you wanted. That's the reason you need to understand all the basics of laws. I would say not the partial differential equations, but the reality. Say, for example, the Bernoulli's equation says the flow should happen. The one principle is the flow should happen, the flow should go from high pressure to low pressure. That's one thing. Is it validating your results? Are you validating those results? Are you able to see those results in your simulation? That's how you need to understand. And those physics, those understanding from the physics will help you to understand the results. If you don't understand the physics, if you're not able to understand what kind of pizza you wanted, whatever end product you will get, you might be amazed, like, what is this? I didn't expect this kind of taste. What I got is something different what I was thinking or I was expecting. So those things, if it doesn't have a proper match, a chain reaction, if it doesn't have a proper match, you will not at all get anything what you require. And that's where you will be not able to understand whether your results are correct or not correct. So let's now little bit talk about the flow physics, whatever we talk about. So the first thing is the Bernoulli's principle. As I said, the simple thing is in that is the flow governing equation. You can understand. I'm not going into the detail of how what Bernoulli's equation is. Everyone knows. Everyone has studied during their the graduation, or in fact in the schooling also. So I understand one thing from the Bernoulli's equation: the flow should happen from high pressure to low pressure. That's one thing I understand. The boundary layer theory, it's the most important. It's the most important part of computational fluid dynamics, because that's what explains the physics. That's where it is governed everything. The interaction of fluid with a solid, the interaction of fluid with the surface of the object, the fluid solid interaction, how the viscosity is playing role. This is the backbone of computational fluid dynamics. Even if I say, if you don't understand the Bernoulli's principle, it's okay. But if you don't understand the boundary layer theory, a lot of things will not be able to understand. Say, for example, if you want, if the viscosity of one fluid is really high and it is flowing over surface, and there is another fluid which has a viscosity less. Now, if we think how the the heat transfer will be, in which case will be higher, or in which case the object will remain for the higher temperature. If you don't understand the boundary layer theory, if you don't understand the interaction of the real fluid with the surface, we won't be able to understand anything. We won't be able to, in fact, understand the results, whether they are correct or not. There is something called the validation of results from your own, whatever you get in the post process. You see, and you try to understand whatever input I gave. I am getting all those things as output, whatever I'm giving, expectation. Are they actually related? You can correlate. You have a certain rules, principles. If you're able to correlate that, best, then your results are good. If you're not able to understand those results, if you're not able to explain those results, no, something is wrong. The flow attachment and separation, that's the, I would say, one phenomena. If you understand the boundary layer theory, it's an outcome, in fact, the flow attachment and separation, but that plays a very major role when we are talking about the aerodynamics. In fact, not just automobile, in fact, the aircraft or any object which is flowing or interacting with the fluid. And then, of course, the type of flow also, which is again where we split the type of flow when we are understanding the computational fluid dynamics. So there are something which is called Reynolds number, laminar flow, turbulent flow. Y plus is some dimensionless number which has some significance. Now, I will not go into the detail of the Reynolds number, laminar flow, turbulent flow, and Y plus, but yes, I will give a glimpse of all these, whatever is in the slide, that how important it is. And of course, the area of interest, if whatever result I want, if it is coming or not. Now, the Bernoulli's principle, again, I'm not going to explain. The only thing what I understand is, if the pressure at A is high and the pressure at B is low, let me get the cursor over there. A here, the pressure is high and the pressure is low over here. So of course, the flow will happen. The flow will govern by the pressure difference, and the flow will go from A to B. That's the simple thing what I understand from the Bernoulli's equation. These things, of course, they're important, but as of now, I'm just taking that into account. Second thing is boundary layer theory. Now, the thing is, the real fluid has a viscosity. Okay, viscosity, we know that's the kind of sticky force. Okay, this kind of sticky force or the friction forces between the layers, and every fluid has a property of getting stick on any surface. If you take any fluid which is, you can rub on your hand, you can feel that it stays on your hand for some time. Okay, so the thing is, every fluid which is interacting with the solid surface, this is the solid surface where you see my cursor. So when the fluid is interacting, what is happening at this level, exactly at the surface, the velocity of fluid will be zero. Why? On the microscopic level, when you will see, there are spikes on the surface. Even though if it is perfectly smooth, you will see some of the spikes on the surface which try to hold the flow of liquid, which try to hold the liquid so that it should not flow. That's called the friction also. So here the velocity will be zero, and as we are moving away from the surface, that effect will be low because the fluid has layers, and those layers slides on each other, and that's where the friction works. So the velocity here will be zero at the wall, at the surface will be zero, and as we are going away from the wall, the velocity variation will happen. Okay, now the velocity the variation will happen up to the extent where you will not have the effect of this wall. That's the most important part of boundary layer theory, the thickness of boundary layer. How far these shear forces can affect the flow, how far from this surface that is effective, how far. And that's the most sensitive area also, where and this is the most sensitive area where the physics is changing drastically, because that's the area where this surface roughness, the surface property or the viscosity of the fluid is playing major role, because that's where it is interacting. Now the flow separation phenomena, which is I'm not explaining in detail, but I'll try to collaborate everything at the end. The flow separation phenomena comes, let me explain you something which is very basic. When you have a curvature, usually, when you have a curvature, if the flow is going from the left to right, initially the pressure will decrease and the velocity will increase from the left to right. Okay. Now, what happened in this case, the flow is attached. Okay. And that what we see in this case, when the flow is going from left to right, the pressure gradient. Now, how we are going to measure that, or how we are going to understand that with the help of pressure gradient. Now, pressure gradient is something very simple. The change of pressure along the surface, or so in first case where we have seen the pressure gradient will be positive. Okay, so when the pressure gradient is positive, the flow will be attached to the surface. The flow will be attached to the surface. So the flow is sticking. Now at this case, when the flow is attached to the surface, the pressure is decreasing and the velocity is increasing. In the next stage, what we have is when the pressure gradient try to become zero. Okay, when the pressure gradient becomes zero, that's where the flow will try to leave the surface, or from the point where it will start leaving the surface. I will explain it how it happens. And then at a point where the flow reversal or flow leaves the surface. Now, one thing I want to make you understand very clearly. Now, let's say in the normal condition at the curvature, when the flow is moving from A to B, the pressure is decreasing and the velocity is increasing. But that's flow attachment, when the flow is attached to the surface. Now, the flow separation phenomena, or when the flow separation happen, what are those conditions? Now, thing is, here we can see the flow is attached to the surface, means the no slip condition, or what we can say is the velocity of fluid at these places are zero. Okay, at these places are zero, at these places they are zero. On the top it is increasing. Now in this case the pressure is decreasing. Now if we can increase the pressure locally, in fact over here the reversal will happen, because the fluid particles which are near the surface, they will try to retard. They are retarding. Okay, the velocity is decreasing, but as the pressure is increasing, okay, so at this area the pressure is increasing, and at this area the pressure is decreasing, and that creates a coupling. And we know the pressure, the flow, from the Bernoulli's principle, the flow will happen from high pressure to low pressure. So basically at this area we have a high pressure, and at this area we have a low pressure, so the coupling will happen. And because the velocity vectors, they have the velocity, the fluid particles, they have the viscosity, so they will try to stick the surface. But because of the Bernoulli's equation, or because of the flow coupling, the flow will start leaving the surface from here. Now this is the phenomena which is called the flow separation, or adverse pressure gradient. At this stage the flow will start leaving the surface, which is very important. So in this case, we have seen how the flow will be attached to the surface. It will not leave the surface. And in this case, the flow will start leaving the surface. So if we see the D point, which is near the surface, and C point, which is just below, just above the surface, and the B point, which is, at somewhere here near the boundary, and A is the free stream over here. So we can see at the C point where flow is retardation is happening over here, and the B point where the flow is accelerating, because it has to follow the conservation law. In fact, the Bernoulli's principle is not applicable when the flow separation is happening. So that's how the flow separation happens, because of the viscosity, because of the no slip condition, because of the change in the pressure. So let's see an example of how the flow separation happens, and how it is important into what I would say, into the industry or in reality. Now here we see we have a wing airfoil. Okay, and by changing the angle of attack, we can see the flow separation, or the flow disturbance is happening on the rear side. Now at this case, now the flow separation is not happening, or the flow separation is not happening in this case. Now when we are changing the angle of attack, we can see at this area the flow is not at all. Now let me pause the video. Sorry, let me pause the video where we can now. Yeah, So we can see at these places, the flow is attached to the surface, and on the top, the flow is attached to the surface. But at this area, the flow is not at all attached. That's called the flow separation from the body. And you can see the effect of flow separation, that it is creating a lot of disturbance in the flow, where we can see it is not at all stable, it is changing drastically. So let's see once more. So we have seen how the flow separation happens when the flow is not attached to the body. But the effect of flow separation is really, it can create a lot of issues. We have seen when the airfoil was 0 degree angle of attack, the flow was pretty much smooth. The downstream flow was very smooth, in fact. But as the angle of attack was changing, we were seeing there is a huge disturbance on the backside of the airfoil. Now, one thing is, if anything is behind that airfoil, if any object is behind that airfoil, in the case where the airfoil has a 0 degree angle of attack, that object which is behind it might not have that much effect. But as the angle of attack is changing, there will be huge disturbance. There will be a huge disturbance on the object which is behind the airfoil, and those effect can be drastic, those effect can be positive, those effect can be negative also. So let's try to see an example of an automobile and try to understand what is the effect of flow separation on that. So let's see, we have a car. Okay, so on the front, we know, I'm not going to explain the physics of this car, but I'll try to make you understand how flow separation is important in this car. So let's say if it is running at very high speed, same as the airflow, the airfoil. So we will have a high pressure in the front of car, because stagnation pressure, because the car is moving, and then the geometry of vehicle is like that when the flow is interacting with the car, it will try to stop the car restriction of the air. So here at the front of the car, the pressure will be maximum. And as the flow is moving along the car, the pressure will change, the velocity will change. Now, I'm not telling whether it will be high or low, because I'm not interested in all. What I'm interested into is the flow is attached to this surface, and slowly when we see, later on when we see that the flow, as soon as it is moving from the front to back, at this areas where you can see the cursor, it is not filled. At this area where you see it is not filled, that means the flow is separated. I'm not going to explain the physics why flow separation happens, but I want to make understand what is the effect of flow separation on that. So from A to B, I would say the flow was attached to the car. From B to C, the flow was attached to the car. From C to D, in fact, the flow was attached to the car. But from D to E and further after, the flow is not at all attached to the car. That should have some negative or positive effect. I don't know. So let's see what are those effects. Now, the movement of car is happening from left to right. Sorry, right to left. Okay, and if we take the steady state, that okay, wind is not moving, wind is stationary, we are moving the car. So the car is moving from right to left, and it is creating a disturbance into the air, or air is creating a restriction of the movement of car. Okay, now the thing is, we have a high pressure in the front of car and we have a low pressure at the back of car. How? Because the when the flow separation happens, when the flow is not able to attach to the car, that's a low pressure, where anyway, I mean, not in that way. If I can simply explain you, the car is interacting with the air, So at this place, the pressure will be higher because the air is trying to stop the car. So at this place, stagnation pressure or the maximum pressure will be there here. At this place, because air is not at all interacting, at these places. So of course, on the rear side of car, the pressure will be lower than what is at the front of car. That's what I can say. Okay, the flow separation, the low pressure is one of the phenomena or one of the outcome of the flow separation. But that's not where I'm going to, not my area of interest. Okay, now, as per Bernoulli's equation, the flow should happen from high pressure to low pressure. Now you see there are two forces which are very much opposite. As per the principle, the flow should happen from high pressure to low pressure. So from left to right. But because the car is accelerating and it is burning fuel, it is creating a pressure. It is creating, the power. So the movement happens from right to left. Okay. Now, when we calculate the drag force of car, we include skin friction drag and form drag, which is called the pressure drag. Now, this difference of pressure is going to play a major role. This difference of pressure. Now, try to understand, the more flow separation, the more low pressure area, and the more form drag or the pressure drag. If you just take, or if you just consider the pressure at point A and pressure at point C, the pressure at point A will be always higher. Now, the thing is, what we can do is to minimize the difference between A and C, because that is directly proportional to the fuel what you're burning, and that's equally, proportional to the mileage of car or, the fuel economy of the car. Now, those things will totally depend on, of course, the fuel consumption, as I said, the vehicle design, that's more important. Now, the vehicle design should be like that there should not be the higher flow separation, minimize, and of course, the vehicle performance. So the flow separation, if we talk, little bit more in details, the flow is interacting with the surface of car at this point where, maybe the geometry of car or the velocity of car is really high, due to which the separation happens. Separation doesn't happen just because of, the pressure gradient. That is one thing how you can measure. But of course, the geometry plays a major role in the flow separation phenomena also. So in this case, we can see we have almost, a curvature over, then we have a slant, we have 90 degrees slant. So the air which is interacting at this places, it's not able to fill the space which is behind the car. That's non-technical way of saying that, you have a low pressure over there. So that's one place where you can see the application of flow separation is very much, very much important when you're taking the fuel consumption of car. This is same kind of principle can be applied to F1 trucks, buses, any automobile if you take. In fact, the aircraft also. But aircraft, little bit the physics is little bit different. There you want more lift and less drag. So that's one different. But the phenomena or the principle remains same across, whether it's aerospace or automobile, it's remains same. So that's the reason why we have seen, Lamborghinis are more sleek, Lamborghinis, and the high speeds car where they are really aerodynamic design, where the flow interaction or the flow separation should be the normal. And SUVs, there is one more reason for SUVs which have the low fuel economy. Not just because of the vehicle structure, but because of the vehicle design also. Now, one more thing is example of flow separation is in SUVs. We have seen, the rear windscreen is always dirty, or sometimes it is very dirty because that's the reason of the flow separation over here. Now, this low pressure area is only near the car, okay, only near the car where interaction is happening. But in ambient, the pressure is much more higher. The pressure is higher. That's 100% sure. Now, I cannot give evidence as of now, but the pressure the pressure which is just behind the car is a bit lower than the pressure which is near the ambient. So of course, again, the flow from the Bernoulli's principle from high pressure to low pressure. Now, In reality, when car is going on the road, there are dust particles, there are sand. So that's the reason why you see sometimes that even the sedans or the hatchback also, the rear windscreens are pretty much dirty if you go into a dusty place, if you go into the places where the roads are not very clean, or if it is windy. That's one more thing, and that's the drawback of the flow separation of the car. It's not just the fuel consumption, but also the vehicle soiling also. Okay, so that's one thing what we have seen. Now next, let's talk about something which is called the type of flow, where we categorize. That's more important when you are when you are trying to understand the computational simulation. Now all these things are still not related to any tool. All these things are related to the phenomena. All these things are related to the physics. We haven't spoke about anything about the tool, neither ANSYS, Fluent, or anything. This is all what we are trying to understand is independent of tool, the physics, and certain laws, or how we can understand first the fluid dynamics. Later on we can see the computational fluid dynamics. Now I'm not going into the detail of what is laminar flow and turbulent flow, but in fact I'm more interested into what's uh, inside the turbulent flow. What's what is how turbulent flow is very critical to handle. So I'm not talking much about the laminar flow. Laminar flow is it's very simple, that low velocity flow, and the velocity vector are quite parallel and stable, and that gives you pretty much stable results. Now, challenging part in computational fluid dynamics, the most challenging part in computational fluid dynamics comes when you start dealing with turbulent flow. It's not like I'm saying laminar is less challenging. No, the expectation with the laminar flows are well established, that okay, this is the flow and that's how the result should be. And a lot of experiments have we have seen that we have a good correlation between experimental and the computational domain. Now, the most important the most complex part in the computational simulation comes when you are dealing with the turbulent flow. Now, the turbulent flow, what I can say is the heights of randomness, or the degree of randomness, whatever you can think, imagine, that's a turbulent flow in the fluid when the fluid is moving. So we can see, like it's really complex. It's not at all the fluid layers are not moving parallel, they're crisscross, they're jumping here and there. So the velocity vectors, where you can see near the wall, it is somewhere here, and all of a sudden they're jumping from here to here. It's highly unstable. You cannot assume, you cannot predict what's exactly happening if the fluid particle is happening from here to here. Of course, it is taking the energy from here to here, so the mixing is also good. But this usually happens at high velocity, not at the low velocity. That disturbance need to have some kind of energy which you need to bring into the flow. Now, boundary layer, we have seen the boundary layer thickness. The boundary layer thickness, we have seen that it's the effect of the wall, or the effect of the the roughness of the wall, up to which extent. So that's what is called the thickness, or the boundary layer thickness. So let's see what is inside the the boundary layer. What exactly is inside the boundary layer? Sorry. So in laminar boundary layer, we have viscous layer, which is usually very much established, or what you can say in the disciplined fashion. But in turbulent boundary layer, which is divided into, you are seeing now the viscous sublayer, and then we have a buffer layer, we have a turbulent region. That's where all the physics, that's where all the challenge, that's where all the the randomness, or the expectation, or the physics change happens, and that's the place where the most challenging part occur. Now let's see how exactly what exactly is inside the boundary layer. So if we have a wall over here, we have then sublayer. Okay, I'm not much interested into what exactly the layer is called, but I'm trying to make you understand what exactly those layers are. Now, the fluid layer, which is exactly on the wall or very near to the wall, the next to the wall, that will have a laminar flow. Okay, because that's highly viscous, that's very high viscous flow, and the randomness will be very less. It will be very stable because it will stick to the surface. Now, the reason behind that is because it will have a maximum effect of wall. The wall will try to grab it, the wall will try to stop it, but because of the inertia, because of the flow, because of the difference in the pressure, or because of the external force, the flow is moving over the wall. So here the inertia in fact is what you say is still dominant because the fluid is able to move, but still the viscous forces are dominant enough to slow it down. Okay, so that's the place where there will not be any fluctuation. In fact, the fluctuation will be very low, and that's the place where the flow will be pure laminar. But that's the place where the shear stress would be the maximum, where the skin friction would be the maximum, where the interaction of the wall with the flow is maximum, where the effect of wall and the fluid interaction is maximum. Now, understood. As we are moving away from the wall, there will be a region where we have a collaboration of a free stream, which is what you say is unaffected by the wall, and the effect of the wall. So it's kind of mixed region where you have both region. Still the free stream is still, one of them is, I would not say dominant, but it's kind of mixed feeling where the turbulent is not maximum, where the wall function is not maximum. It's kind of, okay, let's share it properly, but it's still it has less effect of wall in this region. So in total, this is called the inner region, where you have effect of wall, means dominant. This log layer or the turbulent layer, it has some effect, but it's not fully turbulent. It has some randomness, you can see in the plot, but it's not that turbulent as a free stream or the outer layer. Now, the outer layer is something which is dominant, which is dominant by the fully turbulent. It doesn't, the outer layer doesn't have much effect. I would say the outer layer has minimum effect of the wall. The free stream is something which doesn't have any effect of wall. That's why it could be the turbulent, I don't know. I'm not interested into what's happening on the free stream, but this is the region where the boundary layer has effect, or I would say the effect of viscous forces or the wall, the interaction of fluid with the wall has some effect. So these are the places where the physics changes randomly, the exchange of momentum, the exchange of properties, the exchange of physical parameters happens. That's the place where the physics is more drastic, and it's really hard to understand and predict. So the flow region, we have a free stream, okay, over here, and then we have a turbulent boundary layer, and then of course in the turbulent, again we are subdividing into all these categories. Now, what's happening in fact in the turbulent boundary layer? If we are trying to understand, I'm not going to read all these, the text. The thing is, when we are doing the simulation, why we need to understand all these layers or all these sub layers? Because when we are doing the simulation, when we are converting the computational, when we are converting the real problem, the flow over a plate, the flow over a cylinder, the flow over a vehicle, we need to understand what kind of result you want. Remember pizza theory? So what type of output you want means what type of flow region you want to resolve. You want to resolve this one, you want to resolve the log layer, you want to resolve the outer layer, or you are not at all interested what's happening in the boundary layer. I want to just see, the free stream, how the interaction of fluid is happening, but I'm not at all interested into this. Now, the thing is, every layer has its own significance. Every layer has its own significance and the correlation with the result. Say, for example, if I want to calculate the drag coefficient of vehicle, I will be interested in those sublayer and buffer layer. Question is why and how? The first thing is, when you want to calculate the drag coefficient of vehicle, that means you are interested into two things. One thing is pressure, the variation, the pressure drag or the form drag. The second thing is skin friction drag. Now, skin friction drag is maximum at the wall, where the fluid interaction is happening, where the fluid interaction is happening with the wall, where the fluid interaction is happening with the surface, because that's the place where the friction will be high, where the viscosity will be high, where the shear stress will be high. Most important part. So what I will do, I will search, if I want to calculate the drag coefficient of a vehicle, okay, I need to concentrate on this layer. Again, remember the Pisa theory. What is your requirement? My requirement is drag coefficient, first thing. Second thing is, with that correlation, what I understood, I have to consider the buffer layer or sublayer. With those things, you will be able to understand the setting of solver, the setting of pre-processing, the setting of the input parameter, the setting of the parameters which are directly related to the solver, the type of solver, whether you want K-epsilon, K-omega SST, or you want LES. That's where is the the key point, that you need to understand all these layers properly. If you're not able to understand, if you want a drag coefficient of the vehicle and you're solving for the free stream, you're not all going to get the correct drag coefficient. Second thing, the meshing. Let me go to the next slide. There is some parameter which is called y plus. I'm not going to explain the y plus, but yes, the y plus is directly related to the the mesh resolution, the boundary, the flow, the flow regions. So you can see over here, we are not going to explain it, but still, input parameters. So y plus is something which you do hand calculations to get some value which is directly related to the Reynolds number. I have a slide where I will show the flow process, the CFD process, where how the y plus is important. So in fact, if you're not aware of y plus, you can understand that there is one parameter which is called y plus when you are dealing with a turbulent flow. So I said y plus turbulent flow. So directly when I am saying turbulent flow, so you should get this idea that turbulent flow have all these things. So all regions where I need to get what I am solving. So we can just understand that there is some parameter which has some limitations, which has some categories, that if it is in this range, I am concentrating on this range. If it is some different range, I am concentrating. Now all these parameters are directly related to the meshing. This is what I have, the grids what I am showing is basically a structured mesh what I am showing here. So you see the near wall, you have a fine mesh, and after the wall, we away from the wall, we have coarse mesh. So it's not like you are starting from like this. No, it means if you are concentrating near the wall, you have to have fine mesh, or you have to have a good mesh to resolve everything. And if you are away from the wall, you have to have a coarse mesh. Now the reason is because the energy dissipation or the flux of energy, all these things near the surface is really typical, really hard to simulate, really changing drastically. So all these things we need to resolve properly, and that's the reason there are certain rules when you are following, when you are solving the turbulent flow. If you are not able to understand the turbulent flow properly, you will not be able to resolve the physics, or you will not be able to get the correct understanding or the correct results properly. Let's see a boundary layer example. So this is a typical, what I can say is example of a mesh where we have seen, this is a body where we have generated the boundary layers. In fact, now these boundary layers, you see there is some variation. That's basically a rule of meshing. Again, if we try to understand that, we need to understand the whole meshing process, but that's to capture the physics properly. Now, if anyone asks, if anyone gives me this picture and ask me what type of simulation you're going to do perform on this, the first thing is I will quickly understand, because there are boundary layer simulation. There are boundary layers. In fact, the first thing I understand is they are interested into what's happening near the wall or what's happening near the surface. That means coefficient of friction, or maybe the drag coefficient. So you're trying to simulate the shear stress near the wall. It could be, the heat transfer also. Now the heat transfer, why I said it's more important, because that's the reason where the heat transfer will be the maximum. That's one advantage of understanding the boundary layers theory. This is one place when you are fixing, sorry, not fixing, mixing the flow with the thermal simulation, because that's the place where the flow where the fluid and solid interaction is happening, and that's the place which will where the interface of the solid and the fluid is there. So that's the place where the maximum heat transfer or the heat transfer will be important from one phase of fluid, one phase to another phase. So this is the kind of example where we can see the just seeing the boundary layers or just seeing the mesh, you can understand what type of physics we are interested into. In a lot of what I can say, a lot of interviews or a lot of exams, what can be done is I can give you the screenshot like this, and I can ask you what type of physics are expected. So I can give you option, okay, drag coefficient of the body, the flow patterns and all these things. So to understand that, we have to have understanding of the boundary layer theory or the boundary layers. Now, pre-processing is something which I was talking about, and I said it's not straightforward. It's not just meshing. That's really true. The pre-processing part is something which is related to the geometry preparation, and geometry preparation doesn't mean just to work on the CAD tool. The first thing is you try to understand what is the aim of a study. It's a pipe flow, that means internal flow. It's an external flow, a drag prediction, flow separation. What exactly you're looking for? That's a part of pre-processing. That's an understanding of pre-processing. Now, what kind of physics is involved now? As I said, are you interested into the drag coefficient of vehicle? Are you interested into the conjugate heat transfer modeling? So why I'm always saying that the pre-processing is a part of all these things are part of pre-processing, because you will understand which type of physics are involved. Say, for example, on the basis of second point, if I say what type of physics is involved, if I say, okay, what I want to do is I want to do a conjugate heat transfer, or simply I want to say that I want to see the heat transfer of a block, a solid block, into the fluid. Okay. And there is some external source of air which is cooling. So in all total, it makes a forced convection where we have a heated block, or we have a block which has a high temperature. Now, the important thing is, what do you understand from those parameters, or what do you understand from the physics? Second thing is, once you understand the physics, write down all the important parameters involved into that. That means the temperature difference. When there is a block, there is a solid, that means there is some material, there is the conduction heat transfer, the convection heat transfer. So the first thing you can understand is all the important parameters which are involved into that, so that during simulation you should not miss any of the parameters. If heat transfer is involved, if a solid is involved, what is the material? Material plays an important role because of the conductivity, because of the specific heat. Convection plays an important role, because if it is forced convection, what is the inlet velocity? How much heat transfer coefficient is? What is the temperature difference? What is the area? All these factors are more important, and those comes under the part of pre-processing, where what you can do is write down all the important formulas or governing equations, so that you will be able to understand what are the important parameters when you are setting up the case. You should not miss. You should not miss. You should not miss. That's the important thing, why you should always understand the pre-processing part. It's not just the geometry preparation. It's something which is independent of tool. Then, of course, you need to understand the flow is laminar or turbulent, appropriate calculation, the hand calculation I was talking about. Try to understand what is a Reynolds number. Reynolds number will give you understanding, okay, whether it's a laminar or turbulent flow. If it's a turbulent flow, what is the Y plus value, where we are interested, what is the physics you want to resolve or you want to solve. So those are the parameters, or that's the place. Till I would say, till this place, it is independent of any tool. This makes understanding how much you understood the problem. Lot of places or lot of interviews, they don't ask anything if you're expert in the fluent. No, I'm not at all interested if you're good into the tool and all. Tool is a way where you can set up the problem, but only thing is, how will you know all the important parameters? How will you know which physics is important? How will you know which areas I need to focus on, which is the sensitive area. If you're solving a problem which is related to the conduction, and you're not considering the heat transfer, the conductivity, heat transfer, the coefficient, so conductive heat transfer coefficient. So it might, you don't have a good understanding of the physics. So that's the reason till here I would say you need to understand the physics first. Tool comes later, because tool is something where you're going to enable you, where you're going to put all these parameters. Now from here it starts. Okay, clean up the CAD, close unwanted holes, cracks, gaps, missing surface, all these things, domain definition, all these things are are you capturing the geometry precisely. Those things are related to the tools, which is what you can say is a part of pre-processing, but that's after understanding the physics. Now in the pre-processing also something which is related to the mesh. We are not going into the detail of meshing, that's because that's totally different, in fact a big area. But important part is how you're going to choose the right element size, which is also related to the physics. If you need to understand the size of element, it should not be random. There is a logic behind how you're choosing the size of element to do the meshing. Now let's take an example of, I'll give you a background of why meshing is important. Okay, in fact I will not say meshing. I will try to show a process. I will try to make you understand what exactly happens in computational fluid dynamics, or what exactly how the flow problems are solved. So let's say if I have a domain which is which has certain dimension. I'm not at all interested into what dimension is. It has some finite dimensions. So I have a inlet velocity v1 and outlet velocity v2. So Bernoulli's principle says, of course, the velocity v1 will be higher than velocity v2. Okay, now I have a point A in the domain. I have velocity v1 at the inlet and velocity v2 at the outlet. So if I want to calculate, or if I want to understand what is the velocity at point A, of course this is a constant velocity, this is a constant velocity, the velocity variation is the constant, there is no disturbance in that. So I would say somehow I will get the result something like this at this point, maybe, I don't know. But I would say it's a linear. I'm not interested whether it's a it's different or not. But I would say at this point, from the initial at the 0 to at the L, where the v2 will be higher. So at this point, the velocity at point A, at this situation, the velocity at point B would be linear. Now the thing is, here we are able to understand, or we are able to do a hand calculation of velocity at point A easily. What we can do is we can simply calculate the with some correlation, with some formula. With any formula we can understand the what is exactly a velocity at point A. But what if I insert the object in this, and now I want to study what is the difference in the velocity at point A will come. Now what will happen, in fact what will happen, now the flow is hitting this area, so now this object, and there will be the velocity here, it will not be linear at all. That's one thing I understood. That's one thing I can make sure, because the velocity vectors at this place will not be linear, because here logically the flow is hitting here, so there will be some velocity disturbance, or there will be flow disturbance behind the object. Now if I want to understand the velocity, what is the velocity at point A, what I need to do is I need to calculate the velocities at these points, at somewhere around these points, near these points, and then I'll be able to understand, okay, how much velocity is the at point A when the object is inserted. Now what in that case, maybe the velocity something, it will come like this. So you're not sure, if you are seeing what is the disturbance, because of the disturbance how much velocity is varying, we are not sure whether it will be linear or not. Now what I did to get the velocity at point A, I splitted the domain. Okay, and what I did, in technical terms, I discretize the domain. We have where we have a certain, this is finite distance and x in x and y direction. Now the thing is, this is a finite domain, this is very small domain. Okay, so if I want to do hand calculations, in fact I can do, But what if this domain is really large? If this domain is really, really, really big, the hand calculations is not at all possible. So what we do is in computational dynamics or computational fluid dynamics, the same way split the domain, and the reason to splitting the domain is the same, to understand to get the velocity or any physical quantity parameters, flow velocity, flow, the velocity, or the pressure variation we want to understand at some point. So that's what is the background of meshing. That's what is the reason of meshing. Now I did was structured. There are again the variation in the meshing, so that's where we are not interested, but that's the reason of splitting the domain. Now if I want to if I want to get the velocities at different points, so I have to have what if I want the velocity at the middle of this square or the rectangle. So I need to again split this so that the variation or the point should lie on that, like this it is lying on the node. That's the reason we need to do meshing, and that's the background of splitting the domain. Now let's take an example where we have a car and the meshing has been done on this car. Now the important thing during the meshing, when we are doing the meshing, are capturing all the inputs in the mesh, in the domain precisely. Because see, computational fluid dynamics is something we are simulating a body, or we are doing a virtual test of a finite domain. We have to have a mesh in a finite domain. We cannot have a mesh in infinite domain. We have to have boundaries in which we are simulating. So we have to have the conditions which we are defining, that is the inlet, outlet, and sidewall. That's basically the boundary conditions. But the important part is how well we are capturing the body. That's the area of interest, not this part, not here, not here, not here. That's the area of interest. How we are capturing that and how the mesh transition is happening, that comes into the meshing techniques. But that's how a mesh look like when you're going to solve a problem. Most important parameters of pre-processing in meshing is, are you able to capture the geometry properly? Now, capturing geometry properly doesn't mean you are just capturing all the edges, all the curvature properly. No, it means, are you able to retain the geometry as it is after the meshing, like the CAD? Any distortion in the CAD is happening, any variation in the CAD is happening after you're doing meshing, it should not happen. It should never happen. There are some holes and gaps which are very important into the simulation, so you need to retain that. Are you capturing those holes and gaps properly? There is some sharp edge. Are you trying to retain, or you need that? Maybe that is a critical feature of your geometry. So you have to have, or you have to capture those things properly. That comes under the meshing. Meshing is also one thing where a lot of research has been done, and a lot of research is still going on, so that you can have proper so that you can capture the geometry more precisely and get the more important result. Because again, the mesh is the place where the flow is going to be resolved. Say for example, you are seeing this squares or rectangles at the places where you're seeing the connection. That's the places, or the center of the places, rectangles, the solver is going to solve. At the nodes it is going to solve. So the possibility is that at node A and node B there will be a physics change. So at this point, of course, at this area the physics is not changing drastically, but near the car it is changing drastically. And that's the reason you need a fine meshing to capture the flow physics precisely near the body. That's why we have a fine meshing near the body, and that's why we have a coarse meshing near the away from the body. Because my interest, the area of interest for me, the simulation is the car. What is happening near the car? What is happening? What is the drag coefficient of the car? Not in fact what is happening over here. Okay, so let's go into the process. So this is what I was talking about. This is a flow chart. What can define the complexity. It's way simple. What we see, the input giving velocity, where you are interested, The orange on the top, you're seeing it is independent of the tool. Okay, in fact, the boundary layers, this is all for the understanding. The only part which is a tool is when you create or start calculating the numbers or layers, or when you start doing the meshing. So that's how it's way small. It's, I would say it's it's still, I'm not able to cover this, but if you're able to understand this flow chart, if you're able to understand this flow physics, or if you're able to memorize this, you will be able to understand the CFD process at least 10 to 15%, or I would say not 10 to 15, but more than 20 to 30%. But each and every block has its own complexity. Each and every block, it has its own reasoning, but this gives you a place where you need to think, okay, step by step, what is the process, not just meshing. What is the input? The process is what is the input you have, what you got, and what are the outputs you need based on that. So you need to do some calculation, you need to have some assumptions, you need to calculate some properties. So that's how I tried to summarize the CFD process, which is more or less like, okay, with this you are good to go, but still each and every block you should be able to understand properly. Now, the important part is what we talk about CFD is something that was a background. Okay. The important part is how we are going to understand, how we are going to utilize the skills of our understanding towards computational fluid dynamics. Now here, I have one more slide for the result discussion, and let's talk about the results. This is the simulation or the velocity, u velocity magnitude, and which has been cut at the center of the body. Now you see all the cursors, they are indicating the flow under the body. And if we see sedan, we have sedan 1, sedan 2, and then we have a performance car. Performance car is something you can say sports car. And then we have a SUV, and then we have a truck. Now, one thing we see, there is the geometry variations past B pillar, okay, or the, I can say the back geometry of these cars have different. So of course, what we can expect is the change or the flow behavior in the car, of course. Now, the second thing is the ground clearance of these cars. SUV have a high ground clearance, crew cab truck has a ground clearance, high ground clearance, and we see how this velocity variation is happening. Now, the significance of these results, or how we are going to use these results. The underbody flow in the automobile is very important. There are two reasons. In fact, one is the drag coefficient, because a lot of underbody of automobiles, all the parts are exposed to the airs, and they're very irregular in shape. There are, the axle is open, the suspension, the exhaust is there. But again, the thing is, are you trying to understand the flow physics, or you try to understand the heat transfer? Because if there is the exhaust geometry on the body, there's heat transfer. You want to cool down those parts, or you are only interested into the aero part? You are only interested into the aerodynamic performance of the car. And something we can understand that, okay, SUV is a segment. You can make a SUV aerodynamic, of course, but SUVs are something which are for all the rough terrains, off terrains. So you need to have a high ground clearance. That's the requirement of segment. So the segment you cannot change. The truck, crew cab truck, you cannot change the segment. It has to be like this. Now the challenge comes when you have this kind of body, when you have this kind of geometry, how you can minimize the drag, how you can maximize the cooling of underbody parts, how you can, if you have a performance car, I would not allow the much air to go inside or the underbody. So that's how you can understand the results, and that's how you can, first of all, what is the requirement of for what you were solving. So that way you will be able to understand, this is the reason I was solving. So I want to reduce the drag coefficient of the vehicle from underbody or from the upper body. Now upper body comes from the the looks of the geometry or the looks of the car. So there you cannot do a lot of changes. You have a what you say is you have to compromise with the geometry also. You have a limitations to change the upper body. Now the other part from where you can reduce the drag, maybe underbody, maybe from the wheels, maybe from the pass body, or the what I would say is the trailing edge. So those are the parameters on which you can discuss the results. You can understand for what you ran, for what was the purpose of simulation, and what result you're getting. Now, from this case, from this SUV picture, you can understand there is a lot of flow which is going underbody, and there is a huge low pressure area, or the low velocity, in fact, area. That is the reason the SUV has a high drag coefficients, and in fact the trucks have much more, because again you see the slant here. This is a where this is a generating a low pressure areas over here, and then you have a more underbody flow. But one more thing is, SUVs are not a performance vehicles. They are made for different terrain, so that they can handle off-roading. Trucks are made, these kind of trucks are made for the loading, where you can have a passengers also, and the loading, some of the loading. So of course the segment and the limitations, but in those limitations, how good you are, how much you can help to achieve the good quality of the product. Now in this I would say the consumption of the fuel, or maybe the velocity, which is directly related to the geometry. So these kind of outputs you will be looking for when you're doing a simulation, which is actually important. Now again, the pizza theory, whatever output you want, you have to give all the inputs as per the requirement. That's where you need to understand the physics. That's where you need to understand the domain. If you're looking for aerodynamics of the vehicle, first you need to understand what are the important parameters in the vehicle aerodynamics. Now, second result is something which is performed by Professor Bird. This is very extensive study he has performed. In fact, I would suggest the students to go to his page and search for his studies. He has done a lot of studies on the cyclist, on building aerodynamics, the flow near the building, the flow, the pedestrian safety. He has done a lot of work and experimental study also, and he has very good understanding of these results. These, in fact, he has helped a lot of in lot of races where he has helped these simulations, and those teams they won the races also. It's that important, where you can see the application also. Now in this particular contour, or this in particular snapshot, what we can say is this is a high pressure area over here, because the car is moving and there is a high pressure area in front of cyclists. Now the thing is, if the closeness between the cyclist and the car is very minimum, okay, now this high pressure area is what pushing, okay, and behind the cyclist, what is the pressure? Low pressure area, because of course it is because of the flow separation. Now the flow will go from high pressure to low pressure. That will affect the performance of cyclists. And you might have seen in some races, there are always sidecars which are running with the cyclist, or if there is a marathon, in fact, there are some vehicles. Those vehicles, they can affect the performance of the cyclist. And these kind of races, every single second matters. Every single second matters. Their performance, the way they ride the cycle, you see the posture, it is aerodynamic posture, and the wheel, it has only 3 spokes. The rear wheel is in fact fully covered. So these are the different areas. It's not just the aerodynamics where you can study. It's not just one place where you can study, but there are a lot of areas where the performance matters. In F1, every single split matters when you're going for a lap time. That lap time, if you see, if somebody is following the F1, you see always come into the seconds, and that winner is decided into the split of 1 second. If you are a loser, you are a loser. Once, if that 1 second can decide the result of races. So the physics, the flow, the understanding of those things are that much important. Computational fluid dynamics is not just a tool to do simulation meshing. No, those are the parts. Those are the process you have to do. But how much actually you understand the physics, where you are applying those physics, all those principles, For what benefit? For what, if somebody, the drag coefficient, I remember in my previous industry, where we have achieved the drag coefficient, it was improved by 0.5%, which was very big, which was very big achievement, at least when we are trying for a lot of things and we were not able to achieve. So 0.5, you understand, 0.5 is really small, but when you're calculating the drag, when we are doing studies, that 0.5% is really big, very big for the improvement. Now let's see the module 3, where we'll be talking about the challenges in CFD. What are the challenges? Okay, so let's talk about automobile, which is standing over here, and there are different fields. Now when I was dealing with the aerothermal simulations, I used to deal with the aerothermal simulation where you have to compromise, not compromise, where you have to establish everything very carefully. You have to have a good aerodynamic design, okay, for the less fuel consumption, and you have to have a good flow around the car, in fact the underbody, so that the parts or the any parts which is near the exhaust should not get heated up. So it's between a fight in the flow and thermal, where you want minimum flow so that the drag should be less, but you want maximum flow so that the cooling should happen. So it's like two opposite forces where you have to make a combination, or you need to make establishment where both are good. So dealing with those factors where one is not independent of other, where it's the really challenging, where you are seeing the impacts. Okay, if you have if let's take an example of where you have good aerodynamic design, that will directly correlate the wind noise, because wind noise is something, because the flow is the air is interacting with the truck. So of course the friction or the flow separation, it will create a noise also. Then the vibrations, if the flow separation is too much, that can cause the vibration also. That's very much possible. Crosswind, for the fluid the flow the fuel consumption, the headlight cooling, the stability, and more. So these are the places where you can see it's not straightforward when you're actually going for the product development. It's not that straightforward. Aerodynamics, if we think it's a simple just to make a sleek design, no, not at all. It's way more complex. It's much more complex. If you want to understand how complex it is, try to reduce the drag coefficient of vehicle from the underhood. We have engine, we have a lot of parts, and even if you're able to achieve 1% of that, that's really great. 10%, it's huge. Aerodynamic doesn't just deal with the the aesthetics of the vehicle. It's not just the look of vehicle. Yes, of course, the most important part is optimized design for the best performance, but it's not that simple. The vehicle development, keeping everything ready, the fuel consumption, all the parts should be working properly. All the parts should be in the cooled range. They should not heat up, because heating any part, man, can the damage, it can cause a short circuit, it can cause a fire also. So dealing all those things for the development, or if we just talk about the computational fluid dynamics, if we see manage the the establishment between the thermal and the flow, it's not that easy. Especially for the underhood cooling, it's not that easy. Thermal management of vehicle is not that easy. So what we get is the optimized design, which is that everyone is happy, not very happy, but okay, I'm happy with this thing, because I need to take care of other, I need to take care of my neighbor also, so that he cannot get upset. So it's okay, he is happy, I am happy, both are in the safe range, the vehicle performance is good. That's the aim of the development. Okay, now the challenges in CFD could be, now we are seeing the product development time has changed. If you see about the industries and the competition, most of the industries nowadays they compromise with the cost, time, and the real physics. That's how we see, because of the lot of the assumptions. So the challenges in CFD, what can be done is to speed up the process, where you don't have to wait for much for the results. And still, I remember when I run one vehicle simulation, it takes 18 to 20 hours for a full vehicle, which is really high. Still, 18 to 20 hours is really high. So till that time, I need to understand, what type of physics, or if something goes wrong, again, I need to spend the 20 hours. Automation process, if something is wrong, why can't we just do the update on that? Why we need to run the whole simulation again? That's the one thing I am really interested into. The real physics, again, it's far more complex and unpredictable. We were talking about this along almost like since it's starting. So uh, why we cannot get the exact solution? In fact, there is a method which is called direct numerical simulation. What we see here is DNS and RANs. I did not give any introduction to these things because they are way more complex, and they're basically the schemes, or the solver settings, solvers. But what I can say is, one is that which is calculating for the exact solution, and one is taking the approximate solution. We always go for the approximate solution because this is fast, and this is way more complex, and it is not able to handle the complex geometry. The complex geometry means not just the vehicle. It's not at all for DNS is so far very good for the simple geometry, and it takes a lot of time and effort. So we are still working on approximate solution, not exact solution. The product development time will reduce, the effort will reduce, maybe the testing time for the physical testing will also reduce if we can work on the exact solution instead of approximate solution. Now, but of course, introducing more variables in the approximate solution, it might increase the complexity. You might be able to get something different than what we're expecting. Now, something very important is the real-time simulation. A lot of companies, a lot of firms are still working on this. This will be a game changer, really. If you can, the biggest challenge, the birth of computational fluid dynamics is the flow which we are not able to see, the fluid movement which we are not able to see from our naked eyes. If any industry can do where you can just bring your tablet, just bring your system, and you can see how the flow is happening, that will be a great achievement for the computational fluid dynamics. But that's not that simple as we see in the movies, as we see in the sci-fi or fantasy movies. It's not that simple. It's way much more complex than we think. Now, thing is, what type of jobs, or what type of the opportunities you're looking for if you have a CFD skill, if you do a course, if you do a degree. The basic, or the first most important part, is the meshing. I'm not involving the CAD because that's the designing part, that you're not dealing with the CAD. When you're a CFD engineer, if you have a CFD profile, in fact, you directly start with the modeling. That's the most basic job profile, where you'll be getting as per the domain, you'll be getting the geometries where you need to pre-process it, you need to establish the case, you need to set up the case for the pre-processing. That's one part. Full-fledged could be your work as an application engineer, where you are domain specific, like I am, dealing with the automotive industry. So I don't do the meshing. I deal with the simulations. I see the results, and I try to understand the reports and recommend the results. Other thing is, if you are interested into the development part, if you have a good grip on the coding, you can work on the GUI also. Maybe the solver development, the post-processing development, so testing, validation, and development of the tool also is involved. Research, there are basically two types of research which is based. You're doing a research on the CFD solver, existing method or new methods, or what you're doing is you're taking CFD as a tool and you're doing a research on a product. So basically you're doing a research on the betterment of the product, or you want to make tool better. The future challenge. Now, this is something which is, I would say, the challenge for the industries, for the people also. Now, the product competition, you have seen every automobile company, they're launching 1, 2, 3, 4, 5 cars per year. So of course, the product competition, it's not just car. If you talk about the other technologies also, so that's one thing, product competition. The development cost and time should be reduced. The time, like I said, I still need to wait for 20 hours to get the simulation. so that can be fastened up. And development cost, one more thing is involved is the computational power. You need the CPUs, you need the good machines. It's not at all, it's not like CFD is very the light software. They're really heavy and they need very good very good the computational sources, also the high end system, the high RAM of the system. Now, some of the areas where recently the CFD started working is on the nano and macro technologies also, where we try to simulate, where we try to understand at the nano level or the macro level how that can be changed. In the medical field, recently they started, the best example is the COVID research. I have seen how people are sneezing if they have mask, if they don't have mask. How the ventilation system should be if there is a COVID-19 situation, or if there is any kind of such situation which is the spread can happen. So I've seen these studies doing into the ventilation of the buildings, ventilation of the hospitals. And also recently I started seeing that where the fluid dynamics is collaborated with the structure, and they're doing the simulation of heart, how much the stress on the heart is coming when the fluid is, when the blood is pumped into the heart. So it's really good where where CFD can help in the medical field also, where the human structure, human body is really complex. So, and that we have a web of veins and the blood. So if some the combination or the collaboration with the medical happens, it's really a good research area where a lot of potential or a lot of scope is there. Still there are a lot of disease which are not curable, so which the doctors need a lot of practice. So that can be understood with the help of computational fluid dynamics. Nuclear power, of course, combustion, and the resources, renewable resources, of course. The best example is the electric vehicles. Now we are seeing in last 1 decade, I guess, we have a lot of electric vehicles. Last week, Ola has came up with the Ola scooter to break the stereotype market. And main thing what you see in the electric vehicles is, of course, the lithium battery, but not batteries, but just not batteries, because engine is not there, the powertrain is not there. So there are a lot of design changes in the vehicle, any vehicle, two-wheeler or four-wheeler. In fact, now there is a research going on the industries where we can have the aircraft which are electric. So in that case, see, when we have a fuel, we can increase or decrease whatever is related to. But when we are switching the resource of power, we need to have a lot of reliability, we need to have a lot of validation study on that. So overall, if you see the computational course or computational, what I would say, the degree, or I mean I'm not saying degree or anything, but understanding of computational fluid dynamics from the product development, for the research of the product, or maybe the tool itself. It has a lot of potential. And of course, the CFD is computational fluid dynamics is the industry where it's very narrow. It's in fact very narrow. It's not easy to get the right job. It's not easy because the computational cost is high. The physics, what you're dealing is, you need to be expert. You cannot just it's not about just pre-processing and solving the equations. It's not like that. There are a lot of research you need to understand, predict the results, do the overthinking, and not overthinking, out of box thinking. And overall, it makes a good decision to take this course, because it will make you different. But the thing is, how you're going to make yourself different. Now that thing is to understand everything properly, to understand everything, the physics properly, to understand the tool properties, and tool properly inside out, what is expected. So that way you can make a career, maybe in the research field, maybe as an application engineer, maybe a developer.